Greetings, Science fam. Today we're going to be looking at three different types of reactions: synthesis, decomposition, and combustion. So we're going to start off first of all with our synthesis reactions. And if you remember, for a synthesis reaction, you're really going to have two or more reactants that are going to react and come together to create one new compound. So the thing is, like A plus B gives you AB. So if we look at this, we want to finish our word equation, and then we want to write out and create an entire balanced chemical equation. So first off, I have iron 3 reacts with chlorine. So when iron and chlorine react, since iron's a metal and chlorine's a nonmetal, this is going to be ionic. So it's going to become iron 3 chloride. The reason that we're going to keep that number 3 in there is because if you recall, when we name ionic compounds, iron can sometimes have more than one charge. So for the name of the new compound, that's going to be our iron 3 chloride. And remember, this AB part is right here. That's the iron 3 chloride. The A and the B, in this case, would be the iron 3 and the chlorine. Guess I should have drawn it that way from the B. But there you go. A plus B gives you AB. Now that we have that, we need to start writing out our skeleton equation. So whenever we have iron by itself, even though it's called iron 3, iron by itself is just Fe. If it reacts with chlorine, that means it's going to react with chlorine by itself. Now, if you remember, chlorine by itself is part of Brinkelhoff, which we say are the diatomic molecules. So whenever chlorine is alone, it's never really alone. It's naturally found paired up with itself. So that would be chlorine. Next up is iron 3 chloride. In order to figure out how to draw the compound iron 3 chloride, we need to figure out what the charges are. So we know iron is Fe3+. If you look on your ion sheet, the chloride ion is always -1. It's a halogen. So if we wanted to balance that out, we're going to need 3 of these chloride ions to balance out with the +3 iron. So when we end up writing that, it's going to be FeCl3. That's going to balance it out so they equal 0. Remember, when you're writing ionic compounds, they have to equal a charge of 0. So now that we have that, I'm going to balance this equation. Notice that when I put them together, I just didn't make it iron and Cl2 and just made it at the end FeCl2. It has to be FeCl3 because of the charges of the iron and the chlorine. So that's important, not just to put them together, but to think about, hey, what compound is actually formed? So now that I do that, let's see. I've got 2 chlorines on the reactant side and 3 on the product. So I'm going to make each chlorine 6. So by putting a 3 in front of the chlorine, right, that gives me 6 chlorines. Putting a 2 in front of the iron, that's going to give me 2 irons, but more importantly, it's going to give me 2 times 3 chlorines is 6 chlorines. So now my chlorines are balanced out, which is good. Now I have 2 irons left. The only thing I need to do is put a 2 here to give me those 2 irons. And now that I have that, my 2 irons are canceled out as well. So now I have my finished balanced equation. 2 irons plus 3 chlorines yields 2 iron 3 chlorides. That's nice and balanced and a full synthesis reaction. Okay, so that was a lot of side work and a little drawings in that. You don't have to write all that out, but I wanted to make sure when I went through at least one of them that you kind of saw the little different processes in that. But if you're having trouble with any part, you need to kind of figure out what specific part are you having trouble with. Are you having trouble with figuring out how to write the final compound, like, and balance the, charges out? Are you having trouble writing the words out? Are you having trouble taking these words and turning them into the actual equation? By finding out the little part that you struggle with, that can make it a lot easier and ask specific questions so you can get better at it. Okay, but now from there, let's try the next problem since we've went through this one fully. If sodium reacts with oxygen to yield. All right, well, if sodium's a metal and oxygen's a nonmetal, that means when they come together, they're going to be ionic. So if they come together and they're ionic, we know that we just name them sodium oxide. We don't know how many of oxygens we have yet, but it doesn't matter. When we name ionic compounds, we just simply are going to use the ion names. So now that we have this completed, this A plus B gives us AB, right? A reacts with B to give us AB. Now we can start actually writing out the chemical equation. So sodium by itself is just Na, but oxygen by itself naturally is part of Brinkelhoff. So oxygen is one of those things when we call it oxygen, it really is O2 because it's a diatomic molecule. And then it's going to yield sodium oxide. Now if I look off to the side, sodium, according to my ion sheet, sodium's +1 and oxygen's 2-. So how many sodiums do I need to cancel out with the -2 oxygens? I'm going to need 2 sodiums for every oxygen to make sodium oxide. All right, now that I did that, I'm ready to try and balance. So I'm going to leave my little spots here to balance. Let's see, I've got 2 oxygens on the reactant side, so I need 2 oxygens on the product side. But by doing that, that also made 4 sodiums under here, right? 2 times 2. So I'm going to have to put a 4 there. And I think I'll balance with a 4, 1, 2. 4 sodiums on each side and 2 oxygens on each side of the arrow make this all balanced out. So I have my synthesis reaction completed. Magnesium reacts with oxygen to yield. All right, so I've got magnesium and oxygen are going to react to create something new. Okay, well, magnesium is a metal. So if it's a metal, that means that it's going to be an ionic compound. So this is going to be magnesium oxide. Now that I have that, my next step is to try to start turning this into a chemical reaction. So magnesium by itself is Mg. Some people say, wait, isn't magnesium 2+? Well, that's true. Magnesium does get a 2+ charge when it forms a compound, like over here. But by itself, it's neutral. It's just Mg, magnesium. Now oxygen, if you recall from the last problem, is still O2. It's a diatomic molecule. It's part of Brinkelhoff. So even though we say oxygen, we know that it's automatically O2. Now let's look at magnesium oxide. Magnesium, according to the ion sheet, is +2. Oxide, according to the ion sheet, is -2. So if they're +2 and -2, these guys actually just balance out as MgO because +2 and -2 equals 0. And remember, we always want them neutral. Okay, so now that I have that, let me balance this out. It looks like I have 2 oxygens on the reactant side, so I'm going to need a 2 to make 2 oxygens on the product side. When I do that, now that 2 also made 2 magnesiums, so that means I'm going to have to put a 2 here. And I think I end up with a 2, 1, 2 to balance it all out. Nice and straightforward. But again, if you didn't know that oxygen was a diatomic particle, or molecule, sorry, that could have been confusing. You wouldn't have written that out right, and you wouldn't have had it balanced as well. So keep that in mind. It's important to remember Brinkelhoff, those 7 different elements, right? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. They all naturally pair with themselves. So we just call them their element name, but we assume you know that they all are paired up with themselves in diatomic. The next problem is aluminum reacts with fluorine. Aluminum is a metal, so a metal and a nonmetal are going to make an ionic compound. If that's the case, then we're just going to call them by their ion names. So it's going to be aluminum fluoride. Okay, now that we have that, let's start knocking out our chemical equation. Aluminum by itself is just Al. That happens to be my dad's name and part of my middle name. And then next is fluorine. Remember, fluorine is part of Brinkelhoff. It is a diatomic molecule, so it partners with itself. It's a pair. If we look at aluminum, aluminum charge is Al3+, and fluoride's charge off the ion sheet is -1. So that means I'm going to need 3 of those fluorines to cancel out the +3 aluminum. So when I write that out, it's going to be AlF3 for aluminum fluoride. Okay, now you know the drill. Now that we have that, we have to balance this out. Remember, whatever we start with on the reactant side, we need the same amount on the product, even though they're rearranged. So the fluorines are 2 and 3 on the reactant and product, so I'm going to try to make them both 6. So 3 times 2 fluorines give me 6, and 2 times 3 fluorines give me 6. But in the end, that actually also change the aluminum to 2 aluminum, so I'm going to need to put a 2 there. So it ends up being 232 for our final synthesis reaction. With number 5, we've got calcium reacts with chlorine. Calcium, if you look on the periodic table, is a metal. So if it's a metal, it's going to form an ionic compound. So we are going to call this calcium chloride. We don't have to worry about prefixes or how many of each with mono, di, tri. Doesn't matter because it's ionic. We only use the ion names. So calcium all alone by itself is Ca. Chlorine by itself is Cl2. Did you remember that? Chlorine is part of Brinkelhoff. All right, calcium when I look on the ion sheet is +2 charge, and chloride on the ion sheet is -1. So I'm going to need 2 chlorides to cancel out with the positive calcium. So it's going to be CaCl2. Now that I wrote those out, I need to balance, and it looks like it is already balanced. CaCl2 for both of them. 1 calcium and 2 chlorines on the reactant and product side. All right, our synthesis reaction is done. And just to recap, remember, synthesis is whenever you have 2 or more in the reactant side, but you end up with only 1 compound for the product on the product side. All right, so that was synthesis. Let's move on to decomposition. Here's decomposition. If you think about it, you start with a compound all by itself on the reactant side, and then it's going to break down into pieces. So maybe A plus B, even maybe C if it breaks down even further. All right. The problem is the decomposition reactions are extremely difficult to predict, so we won't be predicting them in class, but you will be able to identify them. For example, here, you're starting with barium carbonate. That's a compound. And then notice it's going to break down into different things, you know. So this is like an A, B, and a C, D, if you will. But in the end, you really did start with 1 compound and broke down into pieces. That's what a decomposition reaction does. So we already have the full word equation. Now we just need to write the chemical equation and balance it properly. And to do that, we need to be able to take the names and turn them into their proper formulas. So let's take a look. Barium is a metal. So if it's a metal, a positive charge, and a cation and an anion, these are going to be ionic compounds. If that's the case, just look up barium's ion on your ion sheet and look up carbonate's ion, CO3, and that is a 2- charge, right? Barium, we still know from earlier, is 2+. If I look up oxide on my ion sheet, it's -2, sorry. And then there's carbon dioxide. That is a covalent compound, and it tells you carbon dioxide means 1 carbon and 2 oxygen. So the name kind of tells you what to do. All right, so now that I have my work written out, let's put these together and actually make compounds. Barium's +2, carbonate's 2-. So these are just going to come together as BaCO3. There's the arrow from the equation. Next, barium 2+ oxygen 2-. This is going to be BaO for barium oxide. And then we have carbon dioxide. Now when we look at that, we want to balance that out. But we've got 1 barium, 1 carbon, 3 oxygen, and 2 + 1 oxygen gives me 3. So this ends up actually being balanced already. So that is now my final balanced equation for this decomposition reaction. But it did take some prep and practice in order to get these compounds together. You did have to look up their charges. So let's just get used to that. For our next one, number 7, we've got magnesium carbonate. Magnesium carbonate, magnesium's a metal. There's no prefixes in any of these names, so these must be ionic. So I'm going to look on my ion sheets. Carbonate is 2-, magnesium's 2+. Magnesium we already know is 2+. Oxide ion is 2-. And then, there's carbon dioxide again. That's CO2. We know because it has the prefix di for dioxide. So now that I know that, I can start putting these guys together. Magnesium's 2+ and carbonate is 2-. So this is just MgCO3. Magnesium and oxygen are +2 and -2, so that's MgO. And then CO2 is the last one. So just like the previous one we did, this ended up being balanced as well. 1 magnesium on each side, 1 carbon on each side, and 3 oxygens on each side. Taking a look at number 8, potassium carbonate. Potassium has a +1 charge. Carbonate has a 3- charge. Potassium +1 charge. Oxide always has a 2- charge. And carbon dioxide we know is CO2. Now that I have my work written out, let's write out my equation. And there's a little typo there. Carbonate is a 2- charge. That's my fault. But if we have potassium, it's +1, you really need 2 potassiums to balance out with the carbonate. So keep that in mind. So when we write potassium carbonate, it's going to be K2CO3 in order to balance that out. Now, when potassium oxide, that's +1 and 2- for oxygen, you're going to need 2 potassiums for every 1 oxygen. And then we already know what carbon dioxide is, CO2. So now that we have that, let's make sure we can balance it. And actually, this one is already balanced. I'm liking these. These are easy. 2 potassiums on each side, 1 carbon on each side, and 3 oxygens on each side. Excellent. Take a look at the next one, zinc hydroxide. Zinc has a 2+ charge if you look on the ion sheet, and hydroxide is OH with a -1 charge. Okay, let me get that minus in there. All right, zinc oxide. Zinc is +2, oxide is 2-. And the last one is water. We know water is just H2O. We don't have to overthink that. Now that we have all our notes, let's start writing out our equations. Zinc is 2+ and hydroxide's -1. So that means I'm going to need 2 hydroxides, -1 and -1, to cancel out with the positive zinc. Now that I have that, I can draw my yields arrow. Zinc +2 and oxygen 2- becomes ZNO, and water is H2O. Let's see how that ends up working out here. Wow, this one balances as well. Awesome. If you don't believe it, take a look. This 2 here goes to the oxygen and hydrogen. So there's 2 oxygens and 2 hydrogens on the reactant side. Well, there's 2 hydrogens and 1 oxygen and 1 oxygen make 2. And then there's 1 zinc and 1 zinc. So this ends up being balanced already, so you can leave it blank or drop 1s in then. Next one might intimidate people at first. They think, whoa, why is there Roman numerals? But remember, iron 2 just means that it tells you that iron is a +2 charge. Hydroxide, if you look on the ion sheet, always has a -1 charge. So iron 2, this is nice. We don't even have to look it up. It tells us what the charge is. Oxide's always 2-, and water we know is just H2O. So now that we know that, we can put these guys together. Since iron is a 2+ charge and hydroxide's -1, you're going to need 2 hydroxides to cancel out with the +2 iron. If you have +2 iron and 2- oxygen, those guys are just going to cancel out. Fe and O, 1 of each, and then water is H2O. Again, let's take a look, but this balances out. How nice. Now, decomposition reactions don't always balance out, but these ones all did. Remember, since this 2 is here, there's going to be 2 hydrogens and 2 oxygens on both sides. 2 oxygens, 2 hydrogens on the reactant side. Iron is 1 and 1, so this balanced out as well. How nice. Really, this is just a testing of, can you read it and put it back into a chemical formula, and then can you balance it? If you can do that, no problem. If you can't, then you got to study up and brush up on naming your ionic compounds. That'll be that simple. The last type of reaction we're going to look at are combustion reactions. Now, we're going to be focused on combustion of hydrocarbons. So, for example, if you ever have a compound that only has carbons and hydrogens and it reacts with oxygen, it's always going to form these 2 products, carbon dioxide and water. In fact, you can add carbon dioxide and water to all of these products on this worksheet. So the only thing we really have to do is balance them out. So let's do that. If I've got, by the way, for balancing combustion reactions, notice how there's oxygen and oxygen in 2 different places on the product side, but oxygen by itself on the reactant side. I would always leave oxygen balance for last. So I would go balance carbon, hydrogen, and then oxygen. That would always be my suggestion. It'll save you some headaches in the end. Okay. If you guys recall, these were also those types of reactions that sometimes we doubled all the coefficients. So let's see if we run into that at all. All right, first is carbon. There's 5 of them, so I'm going to put a 5 in front of there. Next is hydrogen. There's 12, so I'm going to put a 6 in front of there, 6 times 2. Now, let's take a look at how many oxygens we have. We've got 5 times 2, so we've got 10 oxygens, and 6. So 10 plus 6 gives us 16 oxygens. So in order to get 16 oxygens, we need an 8 here. So we're going to balance that out with a 1, 8, 5, 6. Nice. Let's take a look at the next one. 4 carbons, so I'm going to put a 4 here to make 4 carbons. 8 hydrogens, I'm going to put 4 here to make 8 hydrogens. But remember, 4 times 2 is 8 oxygens. 4 times 1 is 4 oxygens. So 8 plus 4 gives me 12. So I'm going to need a 6 there for 6 times 12 gives me, 6 times 2 gives me 12 oxygen. So that became a 1, 6, 4, 4. 13's up next. We have 2 carbon. So I'm going to make it 2 carbon. 6 hydrogen. 3 times 2 gives me 6 hydrogen. Now that I have that, 2 times 2 oxygen is 4. 3 times 1 is 3. 4 plus 3 equals 7 oxygens. Okay. What times 2 gives me 7? Well, it's a number, but it's not a pretty number. It's 3.5. 3.5 times 2 gives me 7. So I am balanced, but the problem is I have a not a whole number. So that's going to be an issue. I can't have a decimal. So if you guys remember, the trick is just to double all the coefficients, because when you double 3.5, it becomes 7. So now it's a whole number. So 1 doubled becomes 2, 2 becomes 4, 3 doubled becomes 6. Now the ratio is still the same and everything's balanced, except now we don't have a decimal point. We have everything a whole number for the coefficients. So 2, 7, 4, 6 balances it out. And last but not least, let's try this. 14, we've got 3 carbon, so I'm going to put a 3 there for 3 carbon. 8 hydrogen, so 4 times 2 is going to give me 8 hydrogen. However, 3 times 2 gives me 6, 4 times 1 gives me 4, so I now have 6 plus 4, 10 oxygens total. 5 times 2 will give me those 10 oxygens, and I now have balanced. Awesome. So these are combustion reactions, because if you notice, let me get a different color here to circle. All of these are hydrocarbons, C's and H's, and they all react with oxygen. If they all react with oxygen, then they always make these 2 products, carbon dioxide and water. That's what combustion is. All right, science fan, way to stick with it and hang in there. Hopefully this makes more sense, and you can now start identifying reactions and also see why we need to learn how to interpret reactions, balance equations, and also write formulas, because it all comes to this point. So good luck, and let me know if you have any questions.